thanks for coming today. I know I'm not a celebrity Android developer, so hopefully you can still enjoy my talk. So today I will be speaking about build times. The title of my talk is How We Brought Down Our Build Times, Modularization Impact of Build Speeds and Metrics. This is a continuation of my talk in DroidCon San Francisco, which was more general optimizations on Android. So I'm going to go through the journey at Pinterest on how we improved our build times. My name is Manuel Nakamurakare, and you can see my Twitter handle, Nakamurakare, and my email in case you have some questions or want to exchange some notes. So feel free to reach out to me. Now this is the agenda for today. I'm going to be talking about Pinterest build times journey, what we had before we started our journey on improving our build times, what we have now, some of our areas of investigation like thermal throttling, frequently modified files. Then I'm going to be talking about some of the metrics that we found were valuable for this to keep track of our progress, in order to find regressions, in order to detect regressions faster. Finally, I will talk about what are some of our next potential steps, and at the end, there will be a QA section. But before I start talking about build times, I want to talk a little bit about my employer, Pinterest. So Pinterest's mission is to bring everyone the inspiration to create the life they love. We also like to think ourselves as the last safe corner on the internet. We have 400 million global monthly active users, 300 billion pins saved, and 3,000 employees. So what you will learn today, so these are basically some of the things that I would like you to take away from my talk today. Modularization, gotchas, and things that you can do to unlock its full potential. Because, a lot of people talk about modularization, how we can improve build times. But just doing that, just modularizing is not going to do the whole, it's not going to give you all the gains that you're expecting. And the other thing is build metrics that will help you to understand the state of your build. So let's get started. Pinterest build times journey. What we had before. So you can see this Slack message describes very clearly the sentiment of our developers. Let's read this just so that we get an idea. Hey, manager 1A, these build times are killing me. I changed a line, and then I want to test my change, and it's taking about 20 minutes to build. So the manager rightfully asks, is something wrong? Are the build times typically this slow? So you can see that this was very bad. I heard rumors that some people were even threatening to quit, right, because things were not very good. Where we are today. So let's read this Slack message. Oh my God, the first time I built the app on my new M1 laptop after cloning the repo was only 5 minutes. Granted, I don't yet have a bajillion Chrome tabs open yet. So you can see that this is like night and day, right? Like very different developer sentiment. So things now look much better. And how did we get there? What did we do in order to get this drastic change? It took a long time to get to this, but what did we do? So we gave new laptop story value, right? Laptops to all developers, and that did the trick. So thank you, folks. That's all my talk for today. No, I'm just kidding. But really, if you can switch to M1 machines, that will help a lot. We know that M1 machines maybe one day won't be as fast, so you can switch to M2s, and then M3s, right? And so on. But sometimes it may be not an option. Sometimes it may not be an option to switch to newer computers, so you still want to see what kind of opportunities you have. And that's how I will want to start our talk for today, which are our main areas of investigations and things that we found. Now, just a reminder that A lot of these was before Pinterest was had availability for A1 laptops. And we were working to modularize our code base, but we still had some big modules. But just like a quick note, I want to talk a little bit about Gradle Enterprise because it's a tool that we use a lot in order to debug our builds and get information. So we use Gradle Enterprise in order to get information from build scans. You can get a lot of debug data. You have this view that allows you to see which are your P50s for your build times, P95. So you can get a lot of stats. You can also get information about how much the different types of cache is saving for your build time. In this view, you can see information for a particular build. So this is called a build scan and allows you to see the timeline of all that Gradle tasks that are running for your build. You can see over here different tasks and how long it takes to execute the task. In this view, you can see avoidance savings, and it tells you how much time you are saving depending on what kind of cache you are using, right? Up to date is the incremental cache, local build cache, and the remote build cache. In this case, you can see a negative value because at least at that time, remote cache wasn't bringing much value. Instead, it was making things slower. And in this view, you can compare. We are comparing two builds so that we can debug why the build cache is not working. So in this case, it gives you information about what's different. This file has different context, which didn't allow you to use the build cache. So now that was a very quick intro to Gradle Enterprise. This talk is not about Gradle Enterprise, right? For that, we have our Gradle Enterprise friends, which you can find them if you want to get more information. So the first part of the talk, I want to talk about modularization, right? Because it's something that a lot of people say, yeah, it's going to help you with your build times. So this was our expectation, right? As soon as we started modularization, we were saying, yeah, like this is going to solve all our problems. Things are going to be fast. And this is how things started. So as you can see, there is a very big task here that takes a lot of time. We have a module called Pinterest. There is not a lot of parallelization going on. And at this time, our P95 was about 9 minutes. P95 basically is describing the worst times that developers can see on their builds. And this is an example of a scan that we got once we were working on modularization. Now you can see that there are many modules that are getting compiled at the same time. We were already expecting to see some gains, but instead, our P95, the worst build times, increased, right? It went from 9 minutes to 14 minutes. That was not expected. And this is how things felt, right? We were expecting to have a super fast car, a super fast build, but instead we got this, things were very slow. So that's when we started digging a little bit deeper into it. And this is some information that we found that was interesting. So in the first row, you can see during the early days of modularization, we had 60,000 lines for our base module. And during modularization, it doubled. So 125,000. So basically, it doubled, right? But then the compilation time for this base module went from 42 seconds to 2 minutes and 30 seconds. So it almost tripled, right? Not just doubled, but tripled. And then we had another module called Pinterest, and this module had almost 400,000 lines at the early stages of modularization, and then it went to 237,000. So it's almost a 40% reduction. And then the build times for this module went from 3 minutes, 42 seconds to 3 minutes and 50 seconds. So roughly the same, right? And this was a little bit confusing for us. We saw that even though Pinterest, for example, had a big reduction on length of code, the build times were almost the same. But for the base module, the lines of code doubled, but the build times tripled. So that was a little bit confusing to us. And that's why we remember that we have been talking with other companies to see what was their build experience, and they were mentioning thermal throttling, right? Basically, your computer gets too hot, and then the processing power gets limited. It hits some limits, and then it doesn't. Things are just not as fast. When we were looking at thermal throttling, we started tracking some values, but the values didn't really provide us information that could help us correlate things. So we started doing some experiments. So for this, what we did was we ran experiments where we used a different number of threads to build the app. So in this case, you can see max workers equals to 1. So that means that we'll just use one thread to build the app. And this is what we got. So when we build the app with one thread, it takes 26 minutes, and there's only one thread here. So of course, it's going to take a longer time. When there are 8 threads, it took 14 minutes, and you can see all the threads here, 1, 2, 3, 4, 5, 6, 7, 8. And then we did another experiment with 16 threads. So it's almost about the same time, right? Like 14 minutes, 13 minutes, it's almost the same. And then based on these experiments, we got this data. So you can see the first column, single thread, the duration of the build times, the second column, the second row, the second column, 8 threads, and the third one, 16 threads. And this column shows the difference between the single thread times and 8 threads. So 5%, 7% when there is no parallelization. So it's roughly the same, and it's also the case for 16 threads. So no major differences in build times. But then when we start looking at tasks that are running with other tasks in parallel, that's when we start seeing more differences. So every time that you see more parallelization, you start seeing that there is a major difference in build times, 45%, 123%, 143%, 141%. And it gets even worse when you use 16 threads, almost 300, almost 250, almost 210. So with this, we got some learnings. Basically, modularization is not a silver bullet, right? Like, just by itself is not going to solve all your problems. It does enable greater parallelization, as you can see, but then it can get limited. The gains can be limited if there is a lot of thermal throttling happening. However, we think that it's still the right thing to do. It's just that you need to get ready. Your code base needs to get ready to do that. And that's when we started looking at frequently modified files, because we started thinking, okay, modularization is helping to have more parallelization, but maybe what we need to do is to try to find what we are building unnecessarily. And in order to do this, to look for the frequently modified files, we use this command that allows you to see all the top 100 files that get modified in the last 6 months. And this is what we got. So on the left, you can see more or less what's the dependency hierarchy that we have in the app. So at the bottom, these are our library modules. For example, design, models, repository. These are things that are supposed to be feature agnostic and shouldn't change too often. Then you have base. Then you have these feature library modules, and then feature modules. So in this dependency graph, ideally, right, like people are making changes to the top modules more frequently so that things don't get recompiled too often, and people are not making changes to this dependency at the bottom, because anytime that you make changes to these dependencies on the bottom, everything on the top is getting recompiled. However, this is what we found. In the top 100 modified files, 45 of those files were in the Pinterest module, in this one, which is fine, right? It's in the top. It's a big module, but still, it doesn't cause full recompilations. The issue was in this. So 52 files were near the bottom of the dependency graph, 25 in base, 25 in libraries, and 2 in the build source, which anytime you make changes in build source, it also causes full recompilations. So our main learning here was that we still had too many changes happening at the bottom of the dependency graph, which is why, even though we were modularizing, almost the whole dependency graph, almost all the modules were getting recompiled, which was causing a lot of thermal throttling, and it didn't allow us to see the gains we were expecting from modularizing. Now, I want to talk a little bit about some common build scenarios so that we can understand a little bit how changes at the bottom of the graph can impact the different common build scenarios. So the first one is local incremental changes. So this is basically any time that a developer is just adding a new feature, adding new methods, and they just try to compile locally. So let's say that they make a change in the common module. This is going to affect almost everything, right? That common is at the bottom of the graph, then that is going to cause recompilations in all these modules, design modules, repository networking base, all these feature library modules, in addition to this. In our case, we still had a lot of feature specific code in the library modules. For example, in networking, we had some retrofit interfaces that were specific to features. In the repository, we also had some data sources that were specific to certain features. So a lot of feature work was still existing in our library modules, which was causing a lot of recompilations. But then this is another scenario. So as we started modularizing, right, we had these feature modules which were sitting at the top. So whenever there are changes at the top here, it's only that feature module that is going to get recompiled. So things are going to be much faster. Another common scenario is when we rebase and build. So in the case of Pinterest, we don't have yet a land queue, which is why it's important that people rebase before they land or before they merge their PRs so that the main branch doesn't break. So in this example, we can see that a developer made some changes at the top in the Pinterest module. But in the main branch, there were some changes in the design library module. So in this case, we have a remote cache available through Gradle Enterprise. So anytime that we land a change in the main branch, this remote cache is going to get populated, which means that these modules are going to be available in the remote cache as well as base, as well as these feature library modules. But of course, not these changes, right? Which means that once a developer rebases, the build is going to be pretty fast since they don't have to compile this, but it's going to be coming from the remote cache, and they just need to recompile this module. So the build time in that situation is going to be very fast. But then we have this example where let's say that we have some changes locally that happen at the library module level, in this case, in the networking module. So in this case, even though there were changes even though a lot of these modules are already available in remote cache, the local build, after you rebase, is not going to be able to take advantage of a lot of those remote cache artifacts because you made changes in networking, which is not available in remote cache yet, and that's going to cause recompilations in all the modules that are depending on it. So this is going to be a slow build. So our main learnings from this were that even though we had started modularizing, a lot of our practices didn't catch up. We were still coding in a very centralized manner. As I mentioned, right, like in networking, we had feature-specific code. In the repository library, we also had that. So that was causing issues. And how can this be solved? So basically, decentralize your library modules and make them feature agnostic. I mean, this is something that we are still working on. It takes a lot of time, right? Because there is a lot of code that needs to be that needs to be refactored, but it's something that is good to set that direction so that developers can start using those practices. Now, example of other things that were not allowing much cache reuse. So we had some random recompilations related to the Jetifier. How did we find this? So basically, what we were doing was we were building the same commit on CI several times, and this is what we found. Sometimes it would take 1 minute, so sometimes it would take 3 minutes, other times 1 minute. So there was a discrepancy in the duration, right? Like there was too much variance. And once we saw that, we used Red Enterprise again to make a comparison of the build scans, and we found that there was this artifact, this jar that had different file content. And how did we solve this? So there are some options here. You could add the offending library to the Jetifier ignore list in case it's possible, or you can try to fix the library. In our case, because I think the use of this library was limited, we just decided to add it to the Jetifier ignore list. And that's how we were able to get around this issue. And this is how you can add the libraries to the Jetifier ignore list. Another cost for limiting the cache reuse was non-deterministic cap-generated files. So in this case, we were seeing some random recompilations, and in order to test that, we found that adding some random unused methods could trigger this. And this is a build scan where we were able to trigger these random recompilations. We saw that even though that method wasn't used, it caused all of these files to have changes, which was causing a cache miss, which was causing a slow build time. And so the next step for us was we started storing these files that were having changes on our CI so that we could see what was changing on these files. And we found that it was the method order that was not deterministic, which was causing, in this case, the cache misses. So in this case, because this library we still needed, we decided to go ahead and fix it. And so we opened basically an issue on Dagger, and then a PR was open, and it was finally landed. So it took a little more time to get this fixed, but it wasn't that bad. I think it took about a week to get all this. Another thing that was causing also not a lot of cache reuse was that the remote cache was getting evicted fast. How did we find this? So one thing that you can do here is that you could build a commit, say on CI that stores the cache artifacts on remote cache, and then once you do that, you can try to build the same commit locally or on CI and try to get the cache key, right? So with the cache key, you can then go and check in Great Enterprise if that build cache entry is available. So this should be available as soon as it gets stored, but then after some time, maybe an hour or 2 hours, you can check again and see if it's present. If it's not present, it could be that you just got evicted, right? And then you have to see how much time you want your artifacts to be available on remote cache. In our case, we had a goal of making them available for 48 hours. And so these are some of the things that we did. We started limiting the number of tasks that push to remote cache on CI. We also increased the remote cache size. We also took a look at which were the tasks that were generating the biggest artifacts, but at the same time, they were very fast to compile, right? So if it's very fast, it doesn't make always sense to store those artifacts. And also, we were only caching on CI the developer flavor so that we don't get too many cache, or we don't get too many artifacts on remote cache. And this is just an example of what we did in order to disable cache for certain tasks. So this is the code. So here you can see the name of the task. So here is a list of tasks. And in this line, we are just saying that it shouldn't be cached. Now, I want to now start talking about metrics. So as I mentioned before, right, metrics were important for us so that we can understand more our builds. We can understand when things are getting better, when things are getting worse, how we can track our progress. In this case, this graph is measuring the percentage of builds that are happening when the base module gets recompiled versus everything, right? So our goal here is that base should recompile less frequently. So looking at this graph, you can see that there is a downtrend, which is positive. And just as a refresher, this is our dependency graph. So because we said that compiling all of these things at the bottom is expensive, right? Since it causes everything at the top to get recompiled. Our goal was to try to reduce the number of recompilations of the base module, because every time the base module is recompiled or anything here is recompiled, base is going to get recompiled. So that's why our goal was to reduce the number of times that base module is getting recompiled. Now, this is another metric. In this case, we are measuring the non-cache compilation time on CI. As you can see here, there is a big drop. And then zooming in, you can see clearly, right, that the build times were about 15 minutes, and then something happened this day or in this commit that made things just faster. After we investigated a little bit, we found that some people had made changes to the min SDK fast dev version, which is basically the developer flavor that we use for our app. So the min SDK was increased, and this allowed us to get faster builds. And we were able to find this information because we were tracking the CI build times with no cache. This metric can also help you to understand how the build times are growing over time, because it doesn't have the noise added by the cache. Now, this is another graph. In this case, we are using a cache. We are using the cache, and the main goal here is to see if cache has any regressions. So in this case, you can see that there is a big drop. So in this case, we made an improvement intentionally. So basically, we found that we were committing the Git branch and the Git SHA, right? So this means that every time that there is a commit, there will be changes in the build source, build config file, which causes cache misses. So the cache was getting dismissed basically on every commit. So after we did this, we saw those improvements that I showed. And this is another metric. In this case, once a day, we build a commit from 1 hour, 2 hours, 3 hours, etc., until 48 hours ago. And with this, what we try to do is we try to measure how fast are the remote cache artifacts getting evicted. So, I mean, I'm just showing a couple of hours. This is a commit done 8 hours ago, and you can see that the P95 in this case is below 2 minutes and 30 seconds. So that's something that is positive. But in this case, it goes all the way up to about 8 minutes. So that means that there is a regression there. And in this case, we found that we had made this change. So in this case, we were testing a different Docker image that had a different JDK. And this was just causing that there were too many artifacts getting stored in the remote cache, which is why things were getting evicted faster. So after we rolled back this change, then we were able to go back to a good state again. Another example of a metric that we found useful was doing some graded profile runs. So graded profile runs, just a quick notice, is a tool that allows you to build allows you to build different scenarios multiple times so that you can see if there are differences in build times. So in this case, we have a scenario that tries to see if there are remote cache regressions. In this case, you see a big bump here. So in this case, we did an investigation and we didn't really find anything unusual, so we just decided to increase the remote cache size. But in this second bump that you can see here, we found that we had done some changes. And basically, this is what we got from Gradle Enterprise, right? We found that this task, the library repository compile fast dev throttling, had some changes here, something that says decorated and with workers decorated. I mean, this is something that I wasn't really familiar with, but it's just telling you, right, that there is something with workers and without workers. So as we dug deeper, we found that we had recently enabled the remote cache for this type of build that has only one worker, but this one doesn't have any workers. So it seems like in this case, Gradle cache was getting confused because it had artifacts built with a single worker versus multiple workers. And he got confused, and that's why remote builds were not able to get hits. So in this case, we just decided to disable pushing to remote cache for that task that has a single worker, and that just fixed the issue. And one more metric, and I think this is the last one, because during all this time, we also started distributing M1 computers. We kept track of these two different metrics. We were keeping track of the build percentage of M1s. So as you can see, right, from January to March, the numbers increased considerably. And this is the effect that it had in our build times. And the reason why it was important to keep track of this was so that we can differentiate what kind of improvements are due to the changes that we are doing in build optimizations versus what's coming from M1s, right? Because we know that M1 laptops cause faster builds. And what were we able to achieve with all these optimizations? So these are our numbers. So P50, which is basically what most developers will see more commonly, was in 1 minute and 5 seconds, or P95, or the worst build times were 14 minutes, 14 seconds. And then back in August, our P50 was 26 seconds, or 60% better, and the P95, 6 minutes, 28 seconds, or 70% better. So as you can see, there was a big improvement in our build times. And what's next? What are some ideas that we have in order to keep improving our builds? We want to keep investing in early regression detection. We want to invest in tooling to prevent regressions. So, for example, have some CI checks that detect build time regressions and then could potentially block the PRs. We want to get a deeper understanding of the build. So we found that Gradle Enterprise is a little bit limited in the kind of queries that you can do. So now we are integrating it with the observability tool Honeycomb and using the Gradle Enterprise API. And we also want to add a LAN queue. The reason why LAN queue is relevant for the remote cache is because when you are using the LAN queue, right, as soon as the PR is merged into the main branch, there is a higher chance, or there is almost guaranteed that the remote cache artifacts will be available with the last commit, which is not something that is available today. So that's all for today, and now I want to open the floor for Q&A.